So hi everybody, I'm really glad to be here today to talk about finding and exploiting an old XNU logic bug. I just hope that you will be able to understand my very charming French accent. So first let me introduce myself. I'm Eloi Benoist-Vanderbeken. I'm working for Synactive, HEXACON organizers. Synactive is an offensive security company. We are 140 experts in the whole company. And I'm one of the reverse engineering team tech lead. The reverse engineering team is a little bit less than 50 reversers, and we work on low-level stuff, so reverse engineering, vulnerability research, exploitation, and so on. We work on everything that has software in it, from bootloaders to a kernel and browsers, well, you name it. In the past, I did a few presentations, mostly about macOS and iOS. As every iOS researcher, I did some presentation, presentation about the latest iOS mitigations. And I hope this presentation will be less depressing. So, what is it about? This year, for Pontoon, there was a new target. It was the MacBook Pro with an M2 system on chip, so with PAC on it, pointer authentication code. The rule was that you had to exploit a kernel bug to get root on the macOS. And the cash price was $40,000. Sorry, it's not much compared to the market, but it's still good to have. So well, I decided to prove to my team that I was good to other things than planning and meetings, and tried to find some bugs. But not. I didn't want to burn any bug. I needed to burn a non-iOS bug because, of course, you don't want to burn an iOS bug to root a MacBook Pro. I didn't want to burn a PAC bypass because those are valuable also. And I didn't want to burn exploit techniques because, as Zerub was saying this morning, well, exploit techniques are very valuable, and Apple tend to patch them also, not just bugs. And you don't want that. Well, I don't want that. Maybe you, as an owner of an iPhone, you may want that, but sorry. So it's actually not that easy because that removes a lot of vulnerabilities, most notably almost all memory corruptions, except maybe some very specific ones where you can logically exploit them by overwriting a string or something like that. But I don't think you will find a lot of vulnerabilities like that in the XNU kernel. So there is not a lot of surface because, as you may know, iOS and macOS shares a lot of code. So if you want to find a macOS only bug, it's not that easy to find something that is only in macOS. There is a quite easy target which is only on macOS. Those are kernel extensions. But as I wanted to do the research on my own MacBook Air, because I do own a MacBook Air, I didn't want to use my company laptop because it's not a MacBook, and I don't want to mix Bounty with professional things. So I decided to do the research on my own MacBooks, but that means no company tools, so no IDA, and I didn't want to use Ghidra because I'm lazy. So no kernel extensions. So when faced to this problem, and sorry, Zerub, if you see this, often the answer is just use logic bugs. Like it was easy to find logic bugs to become root or to escape sandboxes or have arbitrary code execution. So, well, is it really possible to find logic bugs in the XNU kernel to get root? Well, let's find out. There is actually a quite large attack surface, which is in XNU, which is mostly macOS only. This is the file system. Because there is a very large non-iOS attack surface, because on macOS, even as a non-privileged user, you can mount and unmount almost everything. So you can just pick any file, and if the format is supported, macOS will happily mount it. Because on macOS there are SUID binaries, you don't have that on iOS. And because there is almost no sandbox when you're running as an unprivileged user on macOS, if you're not in an application from the App Store, the only sandbox you have is the one enforcing system integrity protection, which is mostly a blacklist and not a whitelist, so almost everything is open. The good thing with a file system is that it's also a source of logic bugs and exploits because of the SUID binaries. Of course, if you can write a SUID binary or create one as root, then you are automatically root. And you can also try to turn UAF into arbitrary file writes. I think there was a couple of Linux exploits that use this because you just have to open a file that you can read and write, maybe free a structure somewhere, and get the structure reused with another file, privileged one, and then you can write in a privileged file, etc., etc. And there is a lot of code in XNU, so no need to get our hands dirty with Ghidra or Radar. So some words about how the file system works in XNU. Well, each file and directory has a vnode. There is a relationship between path and vnodes, which is cached. There is a special rule that every vnode should have only one path, except, of course, for hard links. Vnodes are lazily freed. If you open a file and then close it, even if there are no more references on this file, the kernel will keep the vnode alive because maybe you will open the file in the next minutes or hours. So they only free vnodes when they need it. So it's actually not that easy to exploit use after free on vnodes. That also means that you need to be careful when you are manipulating vnodes because when you just get a vnode, you don't know if it's going to be freed in a few moments or not, so you have to get a reference on it as fast as possible, and you have to make sure that there is no risk of races. So to do that, you have to use the vnode get with a reference or a VID, which is an identifier of the vnode that can be used to make sure that the vnode that you just get hasn't been freed before you get a reference on it. Another thing is that your Unix permissions are cached. That means that if you manage to exploit to use after free into a vnode, that means that if your process already opened the file before, the XNU won't won't check all the permissions by reading the file system. It will trust the permissions that was cached. So that may be a way to exploit use after free in vnodes. Of course, there is a lot of corner cases, but the good thing is that there is a vnode public API because file system developers need to manipulate vnodes to do things and implement their own file format. You understand? And I did, but so there is everything public in the vnode.h. There is a public API that doesn't get changed every day, and there is a lot of documentation also. I did find some bugs, but there wasn't that easy to exploit, mostly because of the lazily free issue of the vnodes. I spent a few weeks during my weekend to try to exploit them, but I didn't succeed. Time was flying, and 10 days before the deadline, 2 days after I said to the team, okay, I gave up, I will just do calendars and spreadsheets, and that will be my new life. I woke up on Saturday morning with my snail that I won't eat. And I thought to myself, okay, let's have a last look to devfd. Why devfd? Because it's a special file system, and I thought maybe there is something that I can do to create arbitrary vnodes, and maybe I will be able to use this to exploit my, my vulnerability. So if you don't know what devfd is, just read the manual. devfd is a little bit like proc self. Oh, I'm not a Linux expert. But, well, you can see all your opens FDs, and you can reopen them by opening them with the devfd pass. So, for example, if you open devfd 0, you will reopen your, the FD 0. It's a little bit like dupe, but you can also choose to change the write. For example, if you have a read-write FD, you can reopen it as read-only or write-only. I don't know why this exists, or if anyone actually uses this, but it's there. I actually already saw the code during my first review, and I thought that there wasn't a lot to exploit in it, because there is actually an ugly hack in Open. When you open a devfd path, you don't get a devfd vnode. Actually, the devfd open function will return a special error, and in the open function, this error will be handled with a special code, which is quite strange because you shouldn't mix the file system specific code into the generic open function, but that's how they do it. And in the end, open will just call the dupefd open function. So this is actually the same thing, the exact same code that you can trigger with the dupe syscall. So I was thinking, okay, cool story, this is quite an ugly hack, but that won't give me root. But actually, the thing is, sometimes you do need a vnode, because this ugly hack doesn't always work. There are other syscalls manipulating paths and not FDs. So for example, what does happen when you call chmod on a devfd file? As chmod take a path as an argument, the first thing that chmod will do is to get a vnode, the vnode of the path, which is a devfd special vnode, which mostly only hold the FD number. Why is that? Because, as I said earlier, there is Apple is trying to keep the one path, one vnode rule. So there is no like processing identifier in the devfd vnode. Then, with this special FD, vnode, sorry, the chmod will first check if the chmod operation is authorized by calling the mandatory access control hooks, so the sandbox, mostly. Then it will call vnode get attribute to get the vnode's bits and owner to check, for example, if the file is not owned by you, and there are no word flags, then you cannot chmod it, obviously. Then after, if all the checks are passed, it will call the vnode set attribute on the vnode to actually change the mode. So maybe you've already got the vulnerability just by seeing the previous slide. But just to be sure, I'm going to give it to you. So how does vnode get attribute and vnode set attribute works? Well, first they call the devfd functions. fdesk get attribute and fdesk set attribute. Those functions will first look up the FD in the current context, so in your process context, to get the file structure, the underlying vnode with fp lookup. Then it will call vnode get attribute and vnode set attribute, but this time on the underlying vnode to get the real underlying bits and to set the underlying bits. So, do you have the vulnerability? Raise your hand. Well, there is an obvious time of check, time of use issue, because you can change the file descriptor between the two calls. You just have to close the FD and reopen anything. And the first vnode get attribute will get the rights, the bits, and the owner of the first FD. And the set attribute will be done on the other vnode, that you have open afterward. So you have to race a little bit to win a race to make it work, but it's quite easy to do. And it can be used to chmod all the files that you can get an FD on. So it's really easy to get root with that. You just have to modify a root file and make it SUID. So you just get write access. You change the mode to get read-write access to the file, and then you make it SUID, and that's it. So it actually took me less than a day to find and exploit the vulnerability, and I started to add a look to devfd code. What took me a lot more time, though, was to create the animated ASCII art right there. And it also took a little bit of time to find the log. I don't know if you can read, but there are a lot of logs lined about exploiting heap buffer overflow and bypassing pack. Of course, this is all fake. Actually, if you see the uname line where I say that this code is running on an M1 MacBook, it's also fake. I run this on an x86 VM. I just patched the uname to make it look like it was executing on on an M1 laptop. But the exploit is real. Okay, this is great. I'm root. I won. I was the only one targeting the MacBook Pro, so I won the cash prize. And the M2 laptop that I'm still using. It's great. I recommend MacBook Pro. And not because I can get root on it. There are excellent machines. Okay, root is great, but SIP and TCC are still in the way. SIP for system integrity protection, TCC for, I don't know. But they block you, they prevent you from reading user documents, from loading arbitrary kernel extensions, and you also cannot modify a lot of system files that are protected with system integrity protection. So can we bypass system integrity protection with the same bug? Let's find out. So what is system integrity protection? As I said, it protects, among those things, it protects system files against arbitrary modifications. Actually, system integrity protection is a very wide system. So it's, this is implemented almost everywhere in the kernel, but one of its functions is to protect system files against arbitrary modifications. Most notably, it's used to protect the kernel extensions related files, the restrictions on the kernel extension that you can load, because Apple is trying to force developers to implement things in user end. So they deprecated a lot of kernel mechanism. For example, before when you were developing an antivirus for macOS, even though there is no virus in macOS, of course, you could use a kernel API to know when files are read, open, or written. Now those API are deprecated, and you have to use daemon userland APIs to get those events. And those restrictions are actually encoded in a configuration file protected by SIP. So if you can write it, you can disable all the restrictions, and you can use all the APIs without being blocked by the kernel extension loader. Another restriction is the user consent. Even if your kernel extension doesn't use any blacklisted mechanism, even if it's correctly signed, the user still have to accept and to whitelist your kernel extension so it can be loaded by the kernel. So it has to go in the system settings, logged as an administrator, and then whitelist the kernel extension. And of course, all this mechanism is protected by SIP, and you cannot modify the consent database. Under the hood, how are those files protected? They are protected with a restricted flag. This is a special flag that you can see with the big O option of ls. As you can see, KX policy, which is the user consent database and the MDM database, is protected with the restricted flag. And remember a few slides back, I said that Mac hooks are called with the DFD vnodes before getting the file attribute. So the sandbox actually only sees this vnode. It doesn't see the underlying vnode. So the sandbox and so system integrity protection has no way to know what the real underlying vnode, because there is no public API that you can feed with a devfd vnode and it turns back the real underlying vnode. So what SIP could do would be to call vnode get attribute to check the restricted flag and then take a decision on that to block the opening of the file. But it would still be exploitable with a race, exactly the same way that we exploited the bug to get root. But actually, it's even simpler than that, because SIP doesn't rely on the restricted flag to block or not the read-write. It's probably a path-based rule. I don't know. I didn't have the time to check. If you know, and if you can tell me, I will be happy to know. But I think it's probably path-based rule. So it doesn't even care if the file has the restricted flag or not. So the exploit is really, really simple. You just open a file read-only, and you change the flags on the devfd alias, and that's it. You bypass the restricted flag. So I'm even sharing with you my L8 exploit. So this is a few lines of ZSH script. It took me actually quite some time to get it, because I'm more a bash user. So what can we do with this SIP bypass? It's actually very easy to bypass user consent. You just remove the restricted flag and then you edit the KX policy database. It's easy to bypass deprecated function detection. As I said, you just have to remove or to edit the kernel extension classification file, playlist file. But it's actually not that easy to load unsigned kernel extensions. It may be possible. I didn't spend too much time on it, but I bricked a few VMs by trying to do it, and I was bored at the end. So if you know how to do it, just let me know. I'll be happy again to know how to do it. But it's still sufficient to load a correctly signed kernel extension and bypassing everything that should be protected by SIP. Just don't forget to kill syspolicy d-demint, so it reloads the file that you modified. Okay. So how has it been fixed? Well, it's quite simple, actually. Apple just added some checks in the devfd code. They, instead of just blindly setting the attributes, now they get the underlying vnode, redo the checks that were done in chmod or chflags, and then set the attribute. It was fixed in macOS 12.6.6 and in iOS 16.5. I gave you the CVE number. It's actually quite strange because iOS shouldn't be impacted. The code is not even compiled in the release kernels. But I guess that if it's in XNU, they suppose that it's affecting iOS. And it was actually in the development kernel that was accidentally released a few months back. By the way, if there are Apple people in the conference, please do release more development kernels. It really helps, and I'm sure that lots of shady companies already have them. So let's just give them to nice companies like us. So to conclude, and let you have your meal, there is no devfd on iOS, and even if it would be very hard to do anything with this bug actually, because you have the sandbox, you don't have any SUID binaries, and even if you add SUID binaries, there would be of no help because the SUID code has been ripped off the kernel, so they are of no use. Of course, there is a mandatory code signature, there are no interpreters, and so on and so on. I won't do the same depressing presentation than zero. Oh, I'm sorry, I don't mean that offensive. It's just as an iOS researcher, it's sometimes hard to hear what we face. It's still a lot easier to get root on macOS, even with PAC, because of course there are, as I said, a lot less sandbox, and okay, maybe the kernel is a little bit, it's hard to hack, but you still have a huge user mode attack surface. Also, logic bugs won't save us all. I don't think we will see logic bugs that give us arbitrary code execution and from the Safari sandbox just like that. But actually, memory corruption neither, because well, they are harder and harder to exploit, as Zerub said. So maybe, and we'll have to do kind of a mix of logic and memory corruption bugs. This is probably why we see so much reports in virtual memory those times. But for how long? Because as you know, when people are starting to hammer an attack surface, it doesn't live very long. So sorry for the depressing last words. And if you have any questions, we may have some time or not. But let me know if you have any question. I'm not so much on Twitter right now because it's getting worse every day. But I still read my private messages, so feel free to ping me on Discord or Twitter, or today or at the party. I will be happy to answer your question or hear your answers to my questions. Thank you.